Let us take a look at the exact solution of this problem. Once we know the exact solution, when we apply our approximate technique, we can see whether we are getting the correct answer. So this equation looks almost like the harmonic oscillator differential equation. This is a second order ordinary differential equation with constant coefficient. And just to remind you, the harmonic oscillator equation just looks like d2x dt2 is equal to minus omega square x. And here instead of x we have psi, and instead of t we have xi. And so this must have sinusoidal solutions which look like this. So it's a linear combination of sine of square root of epsilon times xi and cos of square root of epsilon times xi. Now we impose the boundary conditions. On the left boundary we have psi must vanish, and in that case what we get is b must be equal to 0, because when we put psi is equal to 0, only this term survives and this entire thing becomes just b. That must vanish, and we get b is equal to 0. Now we put in the other boundary condition, the right boundary condition, and we put xi is equal to 1, and in that case we get a sine square root of epsilon, and this must be equal to 0, which means that since if we put in a is equal to 0, the wave function becomes trivial. 0 is always a solution to a homogeneous linear differential equation, but we are interested in non-trivial solution where there is a non-zero probability of the particle being somewhere, and in that case we don't allow this k to be 0, so the sine term must be equal to 0, and that is only possible if the thing inside the sign is an integral multiple of pi. So root of epsilon must be n times pi, which means that epsilon is n square times pi square. Going back to our actual energy, what we can see is this actual energy is n square times pi square times whatever we chose as the unit of energy, which was h bar square by 2 n p square. So this is the actual energy eigenvalue, and the wave functions look like this. We can normalize this wave function, and as I mentioned earlier, the normalization in terms of xi must be integral of psi square from 0 to 1 must be equal to 1 by a, which ensures that the integral with respect to x is 1. So this integral is very easily done. We can use the double angle formula, and we can factor out half and make this 2 times sine square of this thing, which is 1 minus cos of 2 times this angle, and this term integrates to be 0 because at its endpoint the angle changes by an integral multiple of 2 pi, and we get only contribution from this term, and it is just an integral from 0 to 1 d xi, which is just 1. So a square by 2 must be equal to 1 by a, which means that a is square root of 2 by a. So our wave function in this picture becomes square root of 2 by a times sine of n pi x by a, and the energy is just this thing, which is proportional to n square. The proportionality constant is also written here. So let us look at how these wave functions look like. So if we have this as a box, then the lowest order wave function or the ground state wave function just looks like this, and it vanishes at the two endpoints and has one maximum in between, and the corresponding the energy eigenvalue is also the lowest over here. If we increase n by 1, so we choose n is equal to 2, then the wave function looks like this, and the energy is also higher. As we increase n, we get more and more groups like these, and this is for n is equal to 3, and we get something like this. And if we connect these lines, this curve is actually the parabola which is given here, and these are these sinusoidal functions.